All right. Hi, everybody. So as I get started here, I'll start just by telling you, oh, I thought I got rid of this stuff. Stupid clicky thingies. Tell you a little bit about myself. So I'm a professor at the University of Colorado here in Boulder in the Aerospace Engineering Sciences Department. And you can see my history before that. I actually, sort of started my career doing electrical engineering. Maybe some of you guys are also in engineering other than aerospace engineering. And fed into space physics sort of by luck at Stanford. My advisor there sort of recruited me into the group to work on radio wave propagation in the ionosphere, and that's how I ended up in this field. I've been at CU for 10 years now. I also run the graduate program in CU. So if some of you are undergraduates and thinking about grad school, you can feel free to talk to me about what that looks like. And so some pictures of the places that I come from. It's my intro slide. All right, so my research group at CU currently consists of myself, 3 engineers, 8 PhD students. I've lost count on the number of master's students, 2 or 3 master's students, and a varying number of undergraduates, all working on pieces of this puzzle. And it's largely what I look at is the impact of the Earth's radiation belts in the atmosphere and ionosphere. The way we do that is by measuring waves as they propagate through the ionosphere. We measure particles coming from the magnetosphere into the atmosphere, and we measure magnetic fields. And so the group is actually, we have 3 CubeSats that are launching all in February this coming year with 3 completely different missions, but all kind of tied into this general science area. And you'll notice in this center picture, there's a few other things of interest here. There's some X-rays. The little yellow squiggles are X-rays coming back from the atmosphere. And then there's this path here. Oh my, that's interesting. From a transmitter on the ground to a receiver on the ground, which is a way of sensing the lower ionosphere using radio waves. In this case, these are very low frequency radio waves, 10 to 20 kilohertz, which bounce off the bottom of the ionosphere. And we sense that layer of the ionosphere using these radio waves. So we build ground-based instruments to do that measurement while simultaneously measuring everything from above. And doing all the modeling on the left and doing all the instrument development on the right here. So really busy with hardware and data and modeling all at the same time. So this kind of gives you a flavor. The ionosphere is kind of in the middle of this picture. We're actually looking at things from below and from above. And so the rest of today, obviously, I'm not going to tell you all about this research, but actually focus on a little bit of the ionosphere. How many of you have some experience with the ionosphere from classes? Not too many. You've heard of it? Great, excellent. Good. I'm actually happy to hear that because the lecture here is going to start from the beginning. Like, what is the ionosphere? Where does it come from? What is it made of? And then as we get into more detailed stuff, like the different layers of the ionosphere and how those come about. And then Nick asked me to talk about ionospheric variability, so we'll talk a little bit about variations as well. And then being an engineer, I always like to talk about the effects of the ionosphere, in particular on technology like radio communications and GPS. So I'll say a little bit about that, although I have less time than I'm used to, so we'll see how much I can get to. Okay, so to start with, the ionosphere is the layer of the Earth's atmosphere that is ionized. It is not distinct from the atmosphere. They are overlapping. There are neutrals and there are ions in the same regions of space. So we give them different names, but consider it's really just the ionized part of the atmosphere. And it's interesting, any planet with an atmosphere that is near a star will have an ionosphere. You get radiation from the star, in our case the sun, and a fraction of that radiation is ionizing, and so it produces ions. It basically splits neutrals into ions and electrons, and now you've got a charged region of the atmosphere, a charged plasma. So this picture tries to summarize everything about the source of the ionosphere in one slide. So over here on the top left is the spectrum of the sun. And the visible is there in the middle. To the left of the visible is the ultraviolet. To the right is infrared. And the top picture, the top plot in yellow is the black body fit to the curve. The orange is the actual measurement of the sun spectrum. And then the third line below it is what reaches the ground at Earth. So there's absorption in the atmosphere, the difference between the orange and the colorful plot. And that absorption is the sun's radiation being consumed by the atmosphere. Some of that radiation, in fact, most of that radiation is not ionizing radiation. All the stuff from the visible to the right is not ionizing. I'll talk about that on the next slide. But the stuff over here to the left and what you can't see all the way down here at the bottom, ultraviolet, extreme ultraviolet, X-rays, have sufficient energy to ionize neutrals. So that's the source. Now you stick that source into an atmosphere with a composition of different neutral molecules, N2O2, atomic oxygen, argon, helium, hydrogen, nitrogen, you name it. And the different wavelengths of light from the sun will impact different neutrals and cause ionization, create ions. The chemistry between those ions will create new ions, and that's what leads to the ionosphere. All right. Over here on the right is a nice picture that I borrow from Dolores Knipp's book that talks about how the energy sources into the different regions of the atmosphere. And I'll go through this quickly because this is not only the blue square is really relevant for us today, but here's a plot of the temperature profile, approximately temperature profile in the Earth's atmosphere from the troposphere to the mesosphere, troposphere, stratosphere, mesosphere, thermosphere. Which are defined, those four layers, by the way, are defined by the changes in temperature as you increase in altitude. The stratosphere and mesosphere is the region where we have a lot of ozone. Ozone absorbs ultraviolet light particularly well, and so that leads to this heating in that region of the atmosphere. So mesosphere and stratosphere are largely heated by absorption by ozone. The troposphere is largely heated by the light from the sun being absorbed by the Earth, not by the atmosphere itself. The light hits the surface, heats the surface then re-radiates like black body, and that infrared radiation from the Earth, it's sort of like 10 microns, gets absorbed on its way up from the surface, hence the decreasing temperature with altitude. And then finally in the thermosphere, this is where the ultraviolet, the stuff over here from the sun, mostly gets absorbed at the highest altitudes of our atmosphere, above 110 or 120 kilometer altitude. So there's a huge increase in temperature, as you can see, as you go up in altitude from a few hundred kelvins in the bottom part of the atmosphere to 500 to 1500 kelvins in the upper part of the atmosphere. The density is decreasing dramatically, remember. The actual atmospheric density over here is falling off. This laser pointer is wild. Go back. The atmospheric density is falling off exponentially. This is 10 orders of magnitude right here. But the temperature, if I think you heard this in an earlier lecture, is really defining the distribution function of the energy of each of the molecules. It's not the total heat, right? So you have a very high temperature in the thermosphere, even though you don't have a whole lot of density. So the thermosphere is heated by absorption of UV, and over here you can see this description: absorption of extreme ultraviolet, photoionization of oxygen, O2 and N2, photodissociation of O2, that means splitting it into two atomic oxygen atoms, Joule heating, particle precipitation, and waves propagating from below. But that photoionization is obviously the key for today's lecture. Okay, so here's a look at some of how this ionization actually works. Here's another picture of the sun spectrum where it's on a log scale. This is watts per meter squared per meter. So it says watts per meter cubed. I prefer a unit of watts per meter squared per nanometer because that extra unit is per unit wavelength. But this particular plot rolled it into watts per meter cubed. It's not per volume. Just keep that in mind. So here's the visible part of the spectrum and the infrared on a log scale. And then again, over here on the right is all this extra stuff: the soft X-rays, extreme ultraviolet, the far ultraviolet. And those are the ionizing wavelengths over here. To split an atom into an ion and electron takes a certain amount of energy depending on the atom. And that is this plot over here. So for hydrogen, you need 13.6 eV at a minimum, or that corresponds to a minimum wavelength of 91 nanometers to create an ion. So you can draw that line. 91 nanometers is 910 angstroms, so that's right about here. So everything to the left has sufficient energy to ionize hydrogen. And there's different thresholds for different atoms. As you can see, helium has an unusually high one because helium is very stable. So it's really this extreme, this is why it's this extreme ultraviolet and X-ray wavelengths that ionize the atmosphere. Over here on the left is an example of the cross section. I believe this is for N2. And I used to be kind of obsessed with these plots where it shows you various thresholds. You know, the things that can happen when when an atom absorbs light are ionization, which is the red curve. Dissociation, like I said, so say N2 splits into 2 nitrogen atoms, and that's the solid black curve. Or excitation, meaning an electron just gets excited to a higher level, and maybe it relaxes and emits a photon, such as air glow. And that's the dashed black curve. So again, the ultraviolet is the wavelengths of interest, wavelengths that produce this ionization. This part of the sun's spectrum, the visible and infrared, is very stable. If you look at plots over decades, it changes by less than 1%. But this part of the spectrum is extremely variable. This is the part that causes the ionosphere, and it changes dramatically, certainly over solar cycle, over geomagnetic activity, when there are solar storms, et cetera. And so that's what's going to create the ionospheric variability. Okay, so into the actual ionosphere. So here is, again, kind of a picture that nicely summarizes all of these pieces. You've got the temperature profile of the different regions of the atmosphere. You've got the composition of the atmosphere over here in the yellow, green, and blue plots, and the different wavelengths coming from the sun. And they've kind of semi-quantitatively show where those different wavelengths actually penetrate in the atmosphere. And I have a much more quantitative plot of that in a second. So as you know, visible and infrared reaches the ground. And as you go to higher EV energies, they are absorbed higher and higher in the atmosphere. So that extreme ultraviolet that causes ionization is absorbed up here in the thermosphere. X-rays are kind of a weird exception. They do actually make it down into the mesosphere and cause ionization in the D region of the ionosphere. And I'll get to that a little bit more at the end. And so that ultimately the absorption of these wavelengths produces a layer of electrons and ions. And so here's one of many plots that I'll show you of ionosphere density profiles. The density profile means we're talking about the electron density. We can also show you ion densities like N2 plus and O2 plus and O plus, and I'll show you all that as well. The sum of all the ion densities typically adds up to the electron density, right? There's 1 electron for every positive ion, approximately. We split up the ionosphere into the D region, the E region, and the F region, and sometimes F1 and F2. There's a dramatic difference between day and night. Hopefully that's pretty obvious. It's most of the ionization is coming from the sun. So on the night side, as the Earth rotates into night, the ionosphere largely recombines, and so the density decreases dramatically from this curve to this curve. The D region kind of goes away. That's changing by multiple orders of magnitude. The E region relaxes, the F region relaxes. Densities go down by an order of magnitude or more. And then from solar max to solar min, if you kind of look at the pairs of dashed lines or the pairs of solid lines, so this is the difference between a solar minimum at night and a solar maximum at night, solar minimum in the daytime and solar maximum in the daytime. So just the solar cycle itself increases the output of ultraviolet radiation from the sun, again, by close to an order of magnitude. And we see a dramatic increase in the ionospheric density. Okay, and I'm going to talk about the source of all these different layers here shortly. By the way, I should say, if you want to interrupt me with questions, I'm always happy to take questions as well. Great. Okay. So normally when I give this lecture, it's actually in like 4 hours, spread out over multiple days. So I write on all the slides. I'm skipping that in the interest of time. So you'll have to deal with my handwriting that's already up here. Here's a plot showing the atmosphere and the ionosphere simultaneously. So it's a giant mess. And this comes from two models, by the way. The atmosphere plots come from EMSIS. Have you all heard of EMSIS? That's not a lot of hands. Okay. EMSIS is a mass spect. What is the bloody acronym? Mass spectrometry and incoherent scatter radar. Incoherent scatter, which are the two ways that they measure the ionosphere to go into the model. But it's the atmosphere. But it's a model of the atmosphere composition and density as a function of altitude. Model. So the solid lines here, you see I've labeled atomic oxygen, N2 and O2. Those are the neutral profiles of the atmosphere. And then on the same scale, I have plotted the ionosphere profiles, which are the dashed lines, except for that one. They're the thinner dashed lines, which come from a model called IRI, the International Reference Ionosphere Model. So first of all, notice the black line here is the electron density that I'm following with the laser pointer. That's my ionosphere. That's my electron density, similar to the plots on the previous slide. The red dashed line here is O+, one of our ions. And then down here below, you'll see these two lines, red and blue, that are O2+ and NO+. So what's interesting here, down at the lower altitudes, between 90 and 150 kilometers, O2+ and NO+ are the dominant ions. The sum of those approximately equals the electron density. As I go higher, above 150 or so, O+ dominates the entire ionosphere. It makes up 99% of the ionosphere density, all the way through the F region. If I go higher, you don't see it on this plot, but they're starting to deviate a little bit. At some point, this guy will take over, which is H+, which is just protons. So at some point above 1,000 kilometers or so, we basically have an electron and proton ionosphere, which merges into the plasmasphere, which is a region in the Earth's magnetic field. The other thing I want to point out to you here then is just the difference between all of these ion and electron densities compared to the neutral densities. So the neutral densities, even in this altitude range, are pretty high, 10 to the 13, 14, 15, 16 per meter cubed. The electron densities peaks at about 10 to the 12. So even up here at the peak of the ionosphere, it is still less than 1/10 of the neutral density. It's called a weakly ionized plasma. So it's still dominated by neutrals. All right. Any questions on this nonsense? Yeah. Super jagged? Oh. Yeah, that's a... Yeah, no, this comes straight from the model, and I've not understood why it's doing this. This particular line is really weird. Yes, I agree. It comes out of the model. You can kind of see the stair stepping in like a weird way that, something weird happened. But it shouldn't do that, obviously. It's not physical. Same thing with the steps going on down here. It may just be that when we get down to these low densities, the numbers are not accurate. Yep. All right. Okay, so I have a couple of slides with equations. You guys aren't going to be tested on this, I presume. So I'll go through it quickly and just give you the key highlights. So here's a repeat of my ionosphere plot, and I've removed all the neutrals at this point now. So that's just the ions and the electrons. The basic principle here is that we have a certain amount of sunlight with an intensity I, which is units of brightness, it's units of watts per meter squared, that is incident on the atmosphere. So consider this horizontal line here to be a layer of the atmosphere. And it's incident at some angle, chi, which is the solar zenith angle. So sun might be directly overhead, or it might be at 45 degrees, or it might even be right at the horizon. So that solar zenith angle, as you can imagine, plays an important role in the production of ions. So some amount of I, the intensity from the sun, will get absorbed in an altitude layer dH, little delta H in altitude, based on the number density at that altitude, the number density of absorbing neutrals, and sigma, which is an absorption cross-section. Okay? Simple. So your change in intensity depends on the absorption cross-section, the number density, the actual intensity, and the step in altitude. So you can then write that out, take n of h and convert it to n of z. So h is along the path, z is altitude. So I'm converting it to altitude, which then gives us dz times secant of h, or secant of chi, excuse me. So you solve this equation just by integrating, and you get that the intensity as a function of altitude is given by this. So the intensity at infinity means above the atmosphere. And then it's exponentially decreasing according to this mess of an integral that's in the exponent. So that's kind of the general form of the solution of intensity as a function of altitude. If we assume that the number density is a simple exponential, which is nominally true for a large part of the atmosphere, then you can plug that into this equation and solve and get this, that I of z is I infinity e to the minus this whole thing, where h here is the scale height of the atmosphere. You guys familiar with the atmosphere scale height? KT over mg. It sort of says how fast is the atmospheric density decreasing by 1 over e, right? So again, all that stuff depends on your number density, your absorption, the atmosphere itself, h, and the solar zenith angle. So I've done this just as a function of altitude, but it's actually and it's a function of solar zenith angle. It's also a function of wavelength, because that absorption cross-section sigma is a function of wavelength. That absorption cross-section depends on the wavelength of the light incident on the atmosphere. It also depends on the different species in the atmosphere. So you can expand this into this more complicated version that's a sum of integrals over species and their different absorption cross-sections, which are a function of wavelength, and so on, right? Ultimately, this whole piece here, this e to the minus something, can be written as tau, which is an optical depth. All right? So all this is just defining how the light incident at the top of the atmosphere is absorbed in altitude. So now I've got this I here that I just solved on the previous slide. I want to figure out how many ions is that going to produce in a given chunk of altitude, right? So that that production is called P, the ionization production rate. And we use units of pairs per meter cubed per second, because every time you get an ionization event, you get an electron and an ion, right? So it's a pair. And the only thing we've done differently here, so you have this intensity that I solved on the previous slide. Now that gets multiplied by the number density of ionizers, neutrals that can be ionized. And then this sigma is now combined into an ionization cross-section. There's an absorption cross-section, but only a fraction of the light that's absorbed actually leads to ionization, right? Some of it goes into dissociation, some of it goes into excitation. So this eta here is kind of an ionization efficiency between 0 and 1. You kind of do the same thing here and solve for P. Sorry, the laser pointer is fun to fiddle with. Plug back in I from the previous slide and solve for P. And then I once again plugged in the n of z to be an exponential in altitude. And now you get this crazy mess. So the production rate depends on the intensity, the ionization ability, the number density. Here's again that exponential atmosphere, e to the minus z over h. And then this other ugly exponential term that has an exponential inside it. And so that's your theoretical ionization production rate. There will be a test, right, Nick? No, I do this because then I plot it. And that's where you actually get a lot of insight, right? So here is exactly what I've just shown you. On the left is I. This is my intensity as a function of altitude. To no surprise, if you just plot that equation that I came up with, here's I infinity, which is 1. I've just normalized it. As you go down in altitude, it starts to get absorbed by the atmosphere. And then at some altitude, it's kind of all gone. It's all been absorbed for a certain wavelength. If we do the same plot for visible light, it would actually come straight down and almost hit the ground at like 0.9 or something, right? The absorption cross-section is much, much lower. Now I take that I and I plug it in and solve for P, and so here's that production rate, ionization rate. And so what happens at higher altitudes, you've got light to ionize, but you don't have neutrals to be ionized. So you don't get ionization. And at the lower altitudes, you've got a lot of neutrals that could be ionized, but you don't have any intensity anymore. It's already been absorbed, so there's no production. And so in the middle, you end up with this peak. And so this is why the ionosphere forms as a layer at some altitude, right? Here are plots for different solar zenith angles, so it shouldn't surprise you that at solar zenith angle of 0, which means the sun's directly overhead, you get the maximum production rate. And as we go to 89 degrees, we get very, very little production, the sun right on the horizon. The plot on the right is just the same plot now in a log scale on the x-axis. And I do this to point out, so you can kind of notice, and I drew it on here, as we increase in solar zenith angle, not only does the density decrease, the ionization rate decrease, it actually increases in altitude a little bit. So the ionospheric layer actually goes a little bit higher. And that's much more obvious to see here on the log scale. At the top, I've put a couple of parameters in here. Z max is the altitude where the peak ionization occurs. And then P max is the peak ionization rate. And so again, just looking at the things that they depend on gives you a lot of insight. The maximum altitude depends on the solar zenith angle. It depends on the number density of the atmosphere. That N0 is from the exponential atmosphere. It's the density at the surface. And the scale height of the atmosphere plays a big role, H. So if I had an atmosphere with a much larger scale height, that means the atmosphere is not falling off as quickly. Obviously, that's going to push the ionosphere higher in altitude. And then the production rate, similarly, if you have a higher intensity, obviously you get a higher production rate. If you have a higher ionization rate, ionization efficiency, you have a higher production rate. A higher scale height actually makes the peak density lower, because again, if you think of this shallower ionosphere, it's going to get spread out in altitude, and therefore the peak ionization rate is not going to be as high. All right. This is what's called the Chapman layer, by the way. Well, sorry, I'm getting ahead of myself. I'll get to the Chapman layer in a second. Okay, so that's just the production rate. The production rate tells you how many new ions are being created per unit volume per second, but it's not the electron density. How do you get to the electron density from the production rate? Well, the electron density comes out of chemistry, and ultimately it's a balance between production and loss. The typical loss mechanism is recombination. An ion and an electron find each other and recombine into a neutral. You're creating ions all the time by ionization, but you're also losing ions and electrons by recombination. So here is a basic equation for the balance of the ionosphere, that the change in electron density per unit time is production minus loss. That's it. And you can solve this properly if you've got all your production and loss terms and see how the ionosphere evolves. But if we just want to look at equilibrium, we can just say that it's not changing, and therefore production is equal to loss. So in the simplest ionosphere, you might have these two equations. You might have that atomic oxygen is being ionized, so gamma represents a photon, to make O plus and electrons. And then your loss term is that O plus and electrons find each other again and recombine into atomic oxygen and possibly release energy as a photon, like infrared or something. And in this loss equation, alpha is the rate constant. If any of you have had chemistry, you remember all chemical equations have some rate constant associated with them. Sort of how fast does this reaction occur? So if I say production is equal to loss, the loss term from this equation is simply given by the number density of O plus times the number density of electrons, i.e. the two components on the left side of this equation, times that rate constant from the chemical reaction. Again, in chemistry, they like to put those things in square brackets instead of number densities, but it's the same idea. So this is my loss term. If this is my entire ionosphere, then the number density of O plus and the number density of electrons are the same. They're equal to each other. So I can actually replace NO plus over here with another NE and say that my loss is alpha times NE squared. Okay? So if production is equal to loss, then production is equal to this, is equal to alpha times NE squared, and I can solve for NE. So my electron density profile is simply the square root of production, P, divided by alpha. And P is that mess of an equation from a couple slides ago. So we can put that back in and do the same thing. Like I said here, I can put NE is equal to the square root of P over alpha. And knowing what P max is, I can actually get a simplified form of this equation. So square root of P max over alpha e to the minus this mess, where Z1 is this term here, et cetera, et cetera. Just trying to make the equation look less of a mess. And so here's the same plots I showed you before for the intensity and for the ionization rate, the production rate P. And then I'm plugging P into here to then get this, the electron density as a function of altitude and solar zenith angle. So they look kind of similar, except now we're actually in units of electrons per meter cubed. So this is a real density. And similarly, there is some peak in electron density corresponding, maybe roughly with the peak of the production rate. And my ionosphere here is decreasing in density and increasing in altitude as solar zenith angle increases. Okay? So this is what's called the Chapman layer. If you have that very simple chemistry where production equals loss, and the loss is simply alpha times NE squared, that's what's called a Chapman layer. Some parts of the ionosphere act this way pretty closely, and other parts do not, as we'll see in just a second. Okay, questions? Okay, so next we'll start to look at the different ionosphere layers. So this was a simple one species ionosphere, the previous slide, one species ionosphere, one layer in the end, because everything was very, very simplified. In reality, we have all these different wavelengths, we have all these different species, we have the different chemistry throughout different layers of the atmosphere, and so it gets somewhat more complicated. Different wavelengths are absorbed at different altitudes by different species. The intensity is wavelength dependent, and the absorption of different wavelengths changes with altitude. So this really cool looking plot on the right, I really love this one, is actually showing you the intensity of each wavelength from 0 to 300 nanometers. And remember, ionization is really 0 to about 90 or 100 nanometers. So it's really just this left part of the plot. As a function of altitude. And it's normalized so that at the top, at 250, you have the full intensity. So I is equal to 1. And at the ground, for all of these wavelengths, I is 0. So a particular wavelength, say 40 nanometers, is getting absorbed between 200 and 130 kilometers. Some other wavelength is getting absorbed in a very narrow range over here, around 100 kilometers, depending on the species that's doing that absorption, right? So we end up with a different spectrum of waves coming through the atmosphere at different altitudes and ionizing different constituents. And so this plot, what they've done is there's contours for the e to the minus 0.5, e to the minus 1, e to the minus 1.5. It gives you a sense of not only the altitude where they're absorbed, but the range of altitudes where they're absorbed. Okay. So what I'm going to do here is actually look at the different layers and show you how the different layers are behaving. Here is a really ugly plot of the ionosphere. I apologize because I cropped some things, but the arrows got left behind. Showing you the ENF regions. Overall, here are the kind of the biggest reactions that we see. The main constituents of the atmosphere are N2, O2, and atomic oxygen. N2 and O2 in the part of the atmosphere below about 100 kilometers. And as you go above 100 kilometers, it becomes largely atomic oxygen, the neutral atmosphere. So naturally, the ionized part of that region is also mostly O+. So here are all the equations for most of the things that happen. You've got ionization of atomic oxygen, O2 and N2 by photons to create electron-ion pairs. Simple. Atomic oxygen being ionized can now react with O2 and do charge exchange to create O2+, or with N2 to create N2+, or with atomic oxygen neutral with N2+, creates NO+ and atomic nitrogen. Those are called charge exchange reactions. And this last one is a very fast and efficient reaction. So atomic oxygen, when N2 gets ionized by the sun up here, and then it encounters atomic oxygen, it will very quickly steal the electron back and create NO+. I talked about recombination. So here are your simple recombination reactions. O2+ finds an electron and dissociatively recombines. So it will actually separate into 2 atomic oxygen atoms. Similarly, NO+ will do the same thing to split into N and O. O+, when it encounters an electron, recombines to create atomic oxygen in a metastable state. What that means is this is an excited state. The electron is in a higher energy shell, but it's only quasi-stable, and will eventually, over some time period, relax back to a ground or lower level atomic oxygen and emit a photon. And this reaction here, the photons that are emitted are typically one of 2 wavelengths, either 630 nanometers or 557.7 nanometers. And those are referred to as the red line and the green line. And if you've ever seen the aurora or air glow, those are the wavelengths we typically see, mostly the green. The green aurora, which is the most ubiquitous, is at 5577. I miswrote it. That says 577. It should be 557.7. Okay? So this is kind of the full set of reactions. And what you could do, if I gave you the time, is kind of match up which of these you think is most likely to happen based on the altitudes that we see on this plot. So in the E region, I already told you it's mostly O2+ and NO+. And so O2+ is coming from ionization of O2 and from charge exchange with O+. NO+ is coming from this reaction. So N2+ gets ionized first because the atmosphere is mostly N2+. But there's not very much N2+ in the ionosphere profiles because it very, very quickly reacts with atomic oxygen to make NO+. So that's my E region, NO+ and O2+. And then, as I said, in the F region, the dominant neutral over here is atomic oxygen. As you can see, order of magnitude higher than O2 and still higher than N2. And so direct ionization of O to create O+ is the main constituent up here. Okay? And you're starting to see on this plot, because it's got a funky altitude scale, how at higher altitudes, H+ is actually starting to take over here around 800 kilometers on this plot. Okay, so I could go through the different regions. I'll do this maybe super quickly. The E region, O2 is much higher density than atomic oxygen. So like I said, those are the dominant reactions. And so you end up with O2+ as one of the main ion constituents. And we're saying here that it's approximately equal to Ne. It's not quite true because there's the NO+ as well. So you can approximately treat this with that alpha times Ne squared term and get this ionosphere profile. So the E region is kind of like a Chapman layer. In fact, if you do include NO+, you can kind of combine the NO+ and O2+ effects together and still get a very good Chapman profile. That's the E region. The F region at higher altitudes is often split into 2 parts. So the F1 layer is the lower part here. You get ionization of atomic oxygen, like I said, some ionization of N2 as well. This laser pointer is wild. The recombination reaction, this one, as I said, is pretty slow. The release of that photons from that metastable state is actually very slow. So charge exchange reactions actually kind of dominate here. And so you end up with all this stuff happening. You get production of NO+ in that region, but then NO+ recombines to create N and atomic oxygen. In the end, the resulting loss term has 2 terms, just like in the E region, an NO2, that's O2+, it's not NO2 plus Ne, it's NO2 plus times Ne, and an alpha 2 times NO plus times Ne. And you can kind of put those together, like I said, and get an alpha times Ne squared term. So again, F1 region is pretty good approximation of a Chapman layer. The F2 region is not a very good approximation of a Chapman layer. It's not really a Chapman layer. Here you get, again, ionization of atomic oxygen, and then through charge exchange, you get O2 plus and NO plus, and these guys. The primary loss mechanism is that the O plus, it's this reaction, O plus combining with O2 through charge exchange. And if NO plus is approximately equal to Ne, the electron density, I can put that in over here, and I have alpha times NO2, the neutral, times Ne. And those two things are not even close to the same density. The neutral O2 and the electron density. So this is not a good approximation. F region is extra complicated because of the various dynamics, diffusion, vertical transport, electrostatic forces, magnetic field. There's all sorts of things that change the behavior in the F region that really make it not behave like this really simple picture. And I'll get into a little bit of that in a second. So lastly, and really quickly, the D region. The D region is a really funny region of the ionosphere, and it's one that I've actually worked on the most in my career. At the lowest altitudes, below 100 kilometers, things get rather hairy. So the D region is known for very low densities. Most of the UV from the sun has been absorbed. The D region is mostly ionized by X-rays and Lyman alpha, one particular line in the UV from the sun. You end up with weird light and heavy positive and negative ions that I'll show you in a second, and some really complicated chemistry. So production is similar. We have N2 and O2 getting ionized just as before. We also have a pretty good density of NO, and NO2 and NO3, and so that produces NO plus directly. And then in the D region, one of the weird things that happens is that neutrals will interact with electrons like this and create negative ions. So these are the ones I would call the light negative ions, O2 minus. And there's NO minus and other stuff like that. And then those guys can actually lose their electron and free it again through these detachment reactions. So O2 plus through interaction with a photon or by colliding with a neutral O2 can free off that electron again. So electrons are constantly getting attached to create negative ions and then detached again. And that's just one of the weird pieces of the ionosphere. So here is a plot that shows, ignore the red curve for now, but N again is just my neutral density in black, and then blue is my electron density, and the blue is following me down this way, over here. And below about 80 kilometers, now I've got positive and negative ion densities. And so those ion densities at these lowest altitudes actually vastly exceed the electron density. So we've got a region of the ionosphere at the lowest altitudes where electrons are not even really relevant anymore. It's mostly positive and negative ions. All right. So my next slide, yes, this is my favorite slide. So like I said, the D region is complicated. We have light and heavy ions. One of the really common things that happens, there's water in the lower part of the atmosphere. There's H2O. And when we get ions, they tend to attach to water relatively efficiently. And they're called water cluster ions. So the H2O sub n means that I could have 6 water atoms and then 1 proton attached to it to create a positive ion. So that means that the chemistry here gets really complicated. We have the light negative ions, we have the light positive ions, the normal ones like N2 plus, and then we have heavy positive and negative ions, with these water cluster ions. So this nonsensical picture here on the bottom is showing you a block diagram of a model that tries to capture all of the chemistry in the D region. So where the E region had maybe 2 or 3 equations with 3 or 4 constituents, now I've got, this is actually not the complete thing. It's actually like hundreds of constituents and thousands of reactions to do a D region chemistry model that's accurate. So you're seeing various molecules in here that have H2Os in them. There's even some CO2s getting attached. Here's an H plus H2O4, H plus H2O3, HNO3. Weird ions that are combining different molecules together. the color coding here, the blue is showing us really just the simplest chemistry you could possibly do. NO plus, N plus, N2 plus, O2 plus, O plus, and electrons. If that was all we had, we could run a chemistry model with that and see what we get. Green is starting to add in like the next level of complexity of more molecules, and then the white is adding layers on top of that. So this model, this has actually come from a paper by some colleagues of mine, and they actually tried to show that as you added more complexity, there's a region where you sort of converge to a solution that's good enough for whatever application. All right, so I just throw this up here to show you that it's very complicated. All right. So that's the D region, that's the bottom, that's all I'm going to say about that for now. We also should talk a little bit about the top. As we go above the F region, the ionosphere will eventually, there's a region that we call the topside ionosphere, which is really just where the density is decreasing, exponentially with altitude. At some altitude above 1,000, it's sort of merging into the plasmasphere. And different people have different definitions of the boundary there. At those highest altitudes, that's where we, above a few 350, 400 kilometers, we're dominated by just O plus for some altitude range. And then higher altitudes will be dominated by H plus. There's less chemistry at those altitudes because the densities are just becoming very low. So there's reactions between molecules are few and far between. So really the layers of the ionosphere behave according to hydrostatic equilibrium, just like the atmosphere does. So that's why you sort of get the separation of atomic oxygen first and then protons at higher altitude. Helium would have a range in there where it's dominant, but there's just not a lot of ionized helium. Okay. So I'll skip over this. This is a nice little summary. I think you guys will have access to all these slides. This comes from Dolores Knipp's book, where she kind of separates the different layers and talks about the key characteristics of them and their key constituents. Just a nice little summary. All right. The last thing before I get to the next part is on temperature. I've mostly talked about density. Yeah, go ahead. Measured? Great idea. I should do that. No, I definitely have, we have some data coming up, yes. Do I have one that just shows the model on top of data? I don't think I do. So that would be great. Yeah, yeah. You can, I mean, the model, you can always, you have to tune the model to match data sometimes. But the general shape, absolutely, yes. For all the regions, at different times, yes. Like, right, Nick? I mean, you can find, if I ran the model right now and I got an E region, an F region, and then I grabbed some data, I guarantee they would not match. But then I could tune what the assumptions in the E region model and make the E region match, or the F region. You know what I mean? So the models tend to be, at least the models that I've shown you, tend to be sort of climatological. They're kind of looking at an average ionosphere under certain solar conditions. But at a given time in a given location, they're actually not particularly good at agreeing perfectly because there's a lot more complexity, obviously. Yeah. There's history to it, and maybe you guys know the history better than I do. It goes back to like Heaviside, right? That named, I think, the E layer first. Yeah, they started with E. Electrons? Electric. Yeah. The electric layer of the atmosphere, yeah. And then as they got obviously up and down, DNF. Naturally. There is sometimes people refer to a C layer. Very rarely these days. Yeah, historical papers, you'll see a C layer sometimes. All right. So I talked mostly about density. I just have this one plot on temperature, which is important to consider as well. At the bottom part of the ionosphere, down here below 110 kilometers or so, everything kind of has the same temperature. And what I'm plotting are the neutral temperatures, so the atmosphere, and then the ion temperatures and electron temperatures, again, coming from the model here. Down at the, like I said, down at the lowest altitudes, there's enough collisions and mixing of everything that everything kind of gets normalized to the same temperatures. So you're seeing the temperature profile poorly plotted, I guess, of essentially following the neutrals. Now you saw in the atmospheric plots, as we go to higher altitude, the neutral temperature reaches some thermospheric temperature, which tends to kind of stay the same in altitude. Ions and electrons are not quite behaving the same way. So here's an electron temperature that reaches a few thousand kelvins in the E region, and then even a few thousand more, even more higher temperature in the F region and above. And again, the ion temperature is also increasing. At those higher altitudes, excuse me, collisions are pretty rare. And so that you don't have that mixing keeping everything at the same temperature. And so the heating of these different species depends on all sorts of weird things that are happening. It depends on absorption of radiation for the UV, for example, convection within these regions, waves that are pushing particles around, magnetic field, the auroral heating from electrons, all sorts of contributions that change these temperatures. So the key here is just the key that I want you to take away from this is just to know that ions, electrons, and neutrals have different temperatures, even though they're occupying the same physical space. And what that really means is that they have different velocity distributions. I wasn't going to say this, but I will because it's fun. They also, at higher altitudes, can have, even the electrons alone can have two different temperatures because they have a temperature along the magnetic field and a temperature across the magnetic field. But we won't get into that today. Okay. All right, so let me talk about some of the key variability stuff. So I'm not going to do any more of the sort of chemistry and physics stuff, and we'll just kind of look at processes here. So there's a lot of variability comes from transport and the movement of the plasma through the ionosphere, and I'm really not a great expert to tell you all about all that stuff. Variability comes from the solar wind as well and the solar cycle. So I'll say a little bit about that as well. Here are just some of the contributions that actually cause plasma to move around. We'll say a little bit about winds. So just like in the atmosphere, you have winds that are causing particles to move around. Wind arises from temperature gradient, and so the plasma will essentially be pushed along. When there are winds in the neutrals, they actually will drag the ions with them. But then the ions want to move in different directions because of the magnetic field. We'll get into that a little bit in a second. You also have drifts. Drifts are different from winds. Drifts are a particular phenomenon in plasma physics that comes from forces on the plasma. Those forces can be due to gravity, they can be due to pressure gradients, they can be due to electric and magnetic fields. And so I'll say a tiny bit about that as well. And so you put all these things together and you get a fairly complicated picture of the spatial and temporal variations throughout the ionosphere. Things move around in interesting ways. Yes? Pressure gradient? That's a great question. Actually, no, I'll show you actually how that works. Maybe I won't. I don't think I have it in the slides, but there is a distinction here. Do I have it? Did you guys, I thought on Bob Ergin's slides earlier, did he show something about drifts, like E cross B drift? Yes, so E cross B drift. Take the E cross B drift. E in that equation is actually, it's a force. You can take E out, E over Q, and put in any other force, and you create a drift due to that cross product with the magnetic field. So you can treat a pressure gradient as a force in that equation. And the drift is different from just, pushing it in one direction. It's kind of pushing it across the magnetic field that causes it to drift perpendicular to the magnetic field. Okay. All right, so I've got a couple of pictures here just to show you some of the variations. So it's difficult to show obviously a three-dimensional ionosphere. So what we're doing is looking down at the map, and we're kind of measuring the integrated electron density in altitude. You guys heard of this before? Yes. Anybody doing GNSS for research? Nobody? No? Oh, that's a shame. It's a big topic in my department. It's not my research, though. GNSS means you're using GPS or other like signals to measure the ionosphere and various other things you can do with it. And so that's actually how maps like this are created. What they do is they use a GPS signal and look at the essentially the rotation of the radio wave through the ionosphere. And that gives you a measure of this integrated electron density from a spacecraft GPS to a receiver on the ground. Anyway, for the purposes of this discussion, just look at this as here's a color plot of integrated electron density and altitude. And there's a big blob here where I have higher density. It's getting up into the green region, so it's around 50 or 60 over this part of the world. And then it's significantly lower, maybe even an order of magnitude lower than the rest of the world. This map it's a snapshot at 7:50 UT, so 8 p.m. in England, which is going to be noon around here. So this is the subsolar point. You're getting the highest density, obviously, below the sun. Over here, it's on the night side, and so it's got the lower density. This is September, so it's also relatively close to the equinox, which means the subsolar point is right near the equator. So if I were to do a different season, you're going to see this thing move around north and south as the Earth wobbles. But generally, you're going to get the peak density in the ionosphere kind of at the subsolar point. Now, there's a lot more structure here, though, right? There's all sorts of interesting phenomena going on. And again, that's just to show you that there's some variability here. So this measurement, I'll just quickly say, referred to as total electron content. So again, it's the integrated electron density in altitude from space to the ground. So it's going to have units of electrons per meter cubed. But you do that integration, you get something like 10 to the 16 or 10 to the 17 electrons per meter cubed. So they created this unit. It's called 1 TeC unit, which is 10 to the 16. So a number here of 50 would be 5 times 10 to the 17 electrons per meter cubed, integrated in altitude. So this is one particular time and date. Here's a different time and date. So now I've got February at 15 UT. So noon is over here. I think that's why I drew the red dot. And you've got a significantly different picture now. There's a lot more structure. There's something going on down here near Antarctica. There's some variability. Okay. Okay, so one of the key differences that we see, this is actually getting back somewhat historical. Even before they were doing GNSS, this was a way to measure the ionosphere. If you remember our typical, I was going to draw, but I can't draw on this thing. Draw right here. So if you imagine our typical electron density profile from previous slides, there's a peak. The peak is sometimes referred to as FOF2. And the altitude where that peak occurs is HMF2. So H is an altitude of the F2 layer. FOF2 is actually in units of frequency, units of megahertz. And what it actually is the plasma frequency. And that is related to the electron density through this equation. So the plasma frequency, omega PE, is the square root of NE times QE squared over ME times epsilon 0. So that's the charge of an electron, the mass of an electron, and the permittivity of free space. Those are all fundamental constants. So it really just depends on the square root of the electron density. And if you want to convert this to a frequency in hertz instead of radians per second, divide this by 2 pi, you can put in approximate values, you put in actual values, excuse me, for these physical constants, and you get this approximation for the plasma frequency in kilohertz of 9 times the square root of electron density in 1/centimeters cubed. So that's what's often plotted. So you're seeing a plot here, for example, of FOF2 in megahertz, but you can directly convert that to a peak electron density. Okay? So this is a common way of measuring the ionosphere. The way this is measured is from something called an ionosonde on the ground. It's a radio transmitter between kind of 1 and 10 megahertz, because that's typically where the peak occurs. And it sends radio waves up to the ionosphere, and it measures what comes back. And the highest frequency that comes back corresponds to this FOF2, because everything above that frequency propagates through the ionosphere and doesn't reflect. I'll get into that a little more later. So these are from a couple of different stations, both of which are in South Africa, where they monitor over the course of 5 days here the FOF2 and the HMF2. So this is the peak density. This sort of corresponds to the peak density over 5 days, and there's the diurnal cycle. And HMF2 is the altitude. So you actually see the altitude here at night initially, and then it decreases when the sun comes up, and then slowly relaxes as you go into sunset. So that's the ionosphere, as I showed you, moving higher in altitude. And so it's higher at altitude at night and then decreases in the daytime, and kind of repeats that cycle. There's your basic diurnal variation of the ionosphere measured from a couple of individual sites. And you notice a bunch of interesting peaks as well, of course. So there's a big peak here that occurred on this particular day at both of these sites. Big increase in density. Don't know what happened. Go back and figure it out. So that's the diurnal variation. What do I have next? So solar cycle is obviously now going to be a huge variation as well. I mentioned that the sun's UV changes dramatically over the solar cycle. So you end up with ionosphere densities that are much, much higher at solar maximum compared to solar minimum. And that's measured here. So here's, again, FOF2 corresponding to a peak density. And for comparison, the solar radio flux, F10.7, have you guys all heard of F10.7? No? A couple of people? So the F10.7 is a measure of the sun's radio wave output at 10.7 centimeter wavelength, which is 3 gigahertz. And the reason roughly 3 gigahertz, the reason they use that wavelength in particular is because the atmosphere is transparent at that wavelength. And so it can be monitored on the ground very easily. And that radio, the intensity of F10.7 has always been very, very well correlated with sunspot activity. And as you can see from this plot, with ionospheric variation. So it's a very, very good proxy that's been measured since the 40s of ionospheric variability. Going back to 1940, roughly 1950, where we have measurements of this. Obviously, we have sunspots even much, much before that. So that's the solar radio flux, matches really well here. Basically, when the solar radio flux increases, the solar UV increases as well. On the other hand, this last plot is something called AP index. And so if you've heard about this in the magnetosphere stuff yet, AP index is a measure of geomagnetic activity, the Earth's magnetic field, responding to things like CMEs from the sun. And it's not a good correlation. AP index is bouncing all over the place, just depending on geomagnetic storms that are not very well correlated with the solar cycle, except that there tend to be more of them during solar maximum. All right. But again, you can kind of see here at the end on the F10.7 plot, this is multiplied by 10. There's about a factor of 2 variation here in that FOF2, a little bit more than a factor of 2, from 60 to 120. And remember, that goes as the square root of electron density. So electron density is actually varying factor of 4 over the solar cycle. Okay, now I'm going to get into a couple of things that are a little different and interesting. Some of the interesting phenomenology. I can't cover everything in ionospheric variability in the amount of time that we have. So I want to kind of hit a couple of really interesting highlights here. So this is a fun one. The equatorial electrojet is this region here, shown in pink, that follows the magnetic equator. So if you haven't seen plots of the magnetic equator before, this is what it looks like. And what is actually plotted here is a current. And so this is a thin current sheet in the ionosphere, confined to about 110 to 130 kilometer altitude. So it's very small in altitude, and as you can see, it doesn't have a huge range in latitude either. It's just wrapping around the Earth. It's a current. And the density of this current sheet in amps per meter is this, so roughly 0.2 amps per meter, which if you integrate the altitude and you integrate the width of it, corresponds to about 100 kiloamp current. So that's a pretty significant current. That current actually drives a magnetic field. If you remember from basic physics, if you have a current in a loop, there's a magnetic field associated with that current, which will point, if the current is going this way, the magnetic field will point downwards on the inside of that loop and create a little delta magnetic field at the surface of the Earth. And it actually changes the magnetic field at the surface about 50 nanotesla. The surface magnetic field at the equator is about 30,000 nanotesla, so it might seem like a relatively small contribution, but it's enough to be important for us to worry about. And it's also, that perturbation is a nice way to actually measure this current. So what's happening is there is a current, and so here's a kind of sort of a cutaway of the Earth. And this direction is north, that direction is south. And in blue, I've drawn a few magnetic field lines. So at the equator, the Earth's magnetic field kind of looks like that, making a torus around the Earth. And this current is propagating in the direction into the page, as shown. And the ionosphere in this region, this altitude region, has some conductivity. So that current is associated with an electric field as well. Like the electric field comes first. So just as a quick step away, here's what the Earth's magnetic field roughly looks like. I don't know how much magnetosphere you've seen already, a little bit. But we like to approximate it as a bar magnet inside the Earth, which means you have a magnetic north and a magnetic south. It forms this dipole, what's called a dipole magnetic field that looks like so. And in the polar regions, you have sort of quasi-open field lines that extend out into space and connect to the interplanetary magnetic field. So if we zoom in at the equator here in this green box, that's what I'm doing here, the magnetic field generally points upwards. It points from the southern hemisphere to the northern hemisphere. And so you have kind of at the equator, you have a horizontal magnetic field pointing north. Okay. So my favorite diagram, everybody else's least favorite diagram. What happens, and this goes through a sort of a 5-step process here. You end up with charge accumulating at the terminator. So the terminator means the boundary between day and night. So you get charge separation between day and night. That leads to an electric field pointing from positive charge to negative charge. That electric field it now interacts with the Earth's magnetic field. So here's what I just showed you on the last slide, except I've flipped it over this way. So north is to the left, south is to the right. And here's that horizontal magnetic field in the ionosphere above the equator. So I have a magnetic field that's horizontal, an electric field that's into the page, and those drifts that Bob Ergun told you about, like the E cross B drift, here's the general equation for a drift. If you plug in F equals QE, you get E cross B over B squared. That drift, the direction is E, can I do the E cross B is upwards. So the plasma actually starts moving upwards, away from the Earth. So plasma will drift from this equatorial region up to some altitude where the E field is gone now, right? And once the E field is gone, there's no more drift. And then you're in these higher altitudes where it's not very collisional. The electrons tend to be confined by the magnetic field, so they'll follow the magnetic field back down into the E region here and here, both directions. So ultimately what you get is this rising plasma that falls back down the field lines, creates enhancements in the density north and south of the equator, and a little bit of a reduction in density right at the equator. So this is referred to as the equatorial anomaly, as the slide says, and we can actually see this in data. So here is an animation of what that looks like, where you have these two ribbons of enhanced density. Now the Earth is rotating, we're going from day to night, but you can see how there's essentially two giant peaks of density and a null kind of at the equator. All sorts of other stuff going on in this plot. This is actually, I believe this was created for the ICON mission, which is a mission currently in orbit, making really cool measurements of exactly this phenomenon, plus a lot more. I was going to talk about icon, but I removed it for time. Again, so that's one of the variabilities, one of the sort of phenomena that occur in the ionosphere. That's one of the equatorial phenomena. There's all sorts of other interesting phenomena at mid-latitudes and at high latitudes and at polar latitudes. Different latitudes of the ionosphere have wildly different behavior due to the magnetic field direction or due to the aurora, or you name it. All sorts of interesting stuff that one could spend a lot of time on. So Nick actually did this last year for me, for this summer school, because a few months more than 1 year ago was this big storm called the Gannon storm. You guys all familiar with the Gannon storm? People are familiar. So one of the biggest geomagnetic storms we've had in centuries, decades, a long time, huge. And so we wanted to see what was the effect on the ionosphere from this storm. So here are a couple of plots from May 10th at noon and May 11th at noon UT of that sort of global TEC again. And this is coming from a model, not directly from measurements. You do see a little bit of that equatorial anomaly effect. You see how there's kind of a split north and south of the equator here, and same thing here. And we're seeing increased density at these high latitudes, high negative latitudes, probably due to aurora and precipitation and so forth. And so there's a lot of interesting stuff going on. I don't have a whole lot to say to explain everything that's shown here, but again, quite a bit of structure and variability. So that's the global map. But then we also looked at altitude profiles of the ionosphere during this time. And again, here's the May 10th on the left and May 12th on the right. And I will say we're not seeing as dramatic of an effect as I sort of expected. But there's something significant. So if I can remember what everything is here, the black curve here is electron density. The green curve is O+, and this one is O2+, I think, this blue one. So here's your E region density, and then here's your F region, of course. And what you can see is that the electron density increased fairly dramatically. Here's the number here is 500,000, oh sorry, 600,000, and here's 700,000. Actually, it didn't change that much, did it? The O+ density did change. It didn't change that much either. What are we doing wrong here? Oh, it's because we're at mid latitudes. Okay, yeah, we wanted to do Boulder because it's Boulder, but we didn't see, there's not a huge difference. Yes. Yeah, I don't remember, was this it's been a year now. The dates are before and after, or are they both during? Do you remember, Nick?
The 10th at 1. That's before, right?
Yeah.
Yeah. And then the 12th is actually in the.
Okay, so we don't have the peak on here. My bad. Yep. But yeah, thanks for reminding me of that. Oh, okay. Oh, awesome. So it's more fresh in your mind. But yeah, you bring up a good point, though. As we look at this particular location, there's not a huge difference in Boulder on these two times. Because here's the 11th, which is closer to peak, right? Yeah. Okay. Sorry about that. Hi, GCM. Could be. All right. So there's much more to this. I love showing this plot, which is, I believe, from the previous decadal survey from 2013, showing you all the different stuff that's happening in the ionosphere. So here's that fountain effect and equatorial anomaly that I talked about, and so much more that I didn't talk about, right? Again, at different latitudes, affected by the sun, affected by the magnetic field, affected by the neutrals, energetic particles, you name it. And so all of these, all the different environments of the heliophysics, of the space environment that you're learning about this week, they're all tied together and they're all coupled together. And it's pretty challenging to sort of look at one system on its own. Okay. All right, so I've only got a little bit of time left, but I wanted to say a little bit about radio waves. So we have to go back and do some more plasma physics, but I'll try to do that quickly. And what I really want to get to is to show you how waves propagate in this plasma environment in the ionosphere, and how they're absorbed, and how that sort of affects how we use radio waves, basically. Okay, so really quickly, this is slide 1 of any plasma physics class, where we're looking at how a plasma is created. So if you haven't seen this before, the basic idea is if you have a neutral plasma, you've got a bunch of electrons and a bunch of ions in the same space. If you could, say, take all the electrons and pull them to one side, as we do here, what's going to happen? Well, you're going to have a region that's negative on this side and a region that's positive on this side, and they're going to be electrically attracted to each other. They're actually going to create an electric field, and there's a force sort of trying to pull them back together. So the electrons and neutral and ions will try to come back together, but in the absence of collisions, they will just go past each other. And then the electric field will be pointing in the opposite direction, and the same thing will happen, and they'll oscillate. And there is you go through this math, you end up with this standard basic second order differential equation for an oscillator, where this is that oscillation frequency. So I showed you this earlier, that is the plasma frequency, which depends on the electron density and these physical constants. So that's the natural oscillating frequency of any plasma that really just depends on the electron density. All right? Now, for radio waves propagating through a plasma, that plasma frequency actually defines the index of refraction of the plasma. For those of you that have done waves, you understand index of refraction. It affects the speed of propagation in the plasma, like so. So the phase velocity of a wave is the speed of light divided by the index of refraction. And so you see that this index of refraction depends on the plasma frequency, and it also depends on the wave frequency, omega. That's my radio wave. And it's got this weird relationship where if the plasma frequency is less than the wave frequency, I have an index of refraction that is at least real, but less than 1. And the phase velocity is actually greater than the speed of light. If the plasma frequency is higher than the wave frequency, this term is larger than 1, therefore n squared is negative, and the index of refraction is complex. And when that happens, well, right at the boundary where n equals 0 is where you get reflection of the wave from a plasma. And when it's complex, you get absorption, because your index of refraction now has a real part and an imaginary part, and that imaginary part corresponds to absorption of the radio wave. Okay, this is the index of refraction in a cold, collisionless, non-magnetized plasma. And when I start adding those pieces back in, it gets much more fun. Okay, but so the basic picture, as I just mentioned, plasma waves, the plasma frequency is directly related to the electron density. If the radio wave is above the plasma frequency, the index of refraction is real, and waves will propagate through the plasma. They might be refracted because the index of refraction is not equal to 1, but they can propagate through. So there are some frequencies that you can use to propagate through the ionosphere. And that FOF2 that I said gets up to maybe 10 megahertz, that's kind of your lower limit on communicating to space from the ground, or vice versa. Hence why we tend to use hundreds of megahertz to gigahertz for communications. Lower frequencies below omega p will refract and reflect off the ionosphere, like so. So HF waves in the few megahertz are commonly used for over-the-horizon communications, because you can bounce off the ionosphere and propagate many thousands of kilometers, actually. We take advantage of the ionosphere, and we take advantage of this plasma phenomenon for the different types of communication. All right? So what are these critical frequencies? I showed you this in the F region, typically a few megahertz, occasionally up as high as 30 megahertz. Higher frequencies will go through the ionosphere. In the E region, typically that critical frequency is just 1 or 2 megahertz. It's typically lower density in the E region. But one of the phenomena that I didn't get to tell you about is what's called sporadic E, where you can end up with extremely high densities in the E region, like 100 times higher than this nominal density. And so sometimes you'll actually get critical frequencies up to 100 megahertz in the E region. So you'll essentially block communications below that, below 100 megahertz. In the D region, this is no longer true. And so things get very strange. And I can show you some of that in a little bit. In the D region, mainly the problem is you have a lot of neutrals. So you can no longer treat it as a collisionless plasma. And that very, very high collision frequency changes the index of refraction and changes the propagation characteristics. And also collisions lead to absorption, which I'll talk about in a second. Generally, though, in the D region, we get reflection of waves below about 100 kilohertz. This is a very low frequency, right, compared to the stuff we've talked about earlier. And so there is a region of frequencies here called the VLF and LF that are actually used for extremely long distance communications. Like over the horizon, that's baby stuff. VLF we use to communicate around the globe. This wave from a transmitter or from lightning bounces off the D region ionosphere and continues to bounce off the ground in the ionosphere all the way around the globe. You can measure these signals at the antipode. In fact, sometimes you can measure them back at the source as they've gone all the way around the globe, depending on how powerful they are. Those are actually used by the Navy. The Navy operates VLF transmitters. This is a big part of my research, hence why I'm going on about it. The Navy operates these transmitters in kind of 20 kilohertz frequency to communicate with submarines. That the transmitter might be in Hawaii, the submarine might be in the South Pacific, thousands of miles away, and they can send this signal, which the other feature of VLF waves is that they will penetrate seawater some distance. And so submarines can actually pick up that signal below the surface. Okay. So when we have a collisions, here is now the new equation for the index of refraction. This is I think it's my favorite equation. Does everybody have a favorite equation? Have to. This is the index of refraction in a cold collisional magnetized plasma. And it's referred to as the Appleton-Hartree equation. And it's actually simplified because it's only for one species. When you start adding in multiple species, it gets even more complicated. What we've done is we've simplified, we've written terms of X, Y, and Z in here. X you can think of as the plasma. So X is just the normalized plasma frequency, which is related to the electron density. Y is the magnetic field. It's the gyro frequency, which is directly related to the magnetic field intensity, and then normalized by the radio frequency again. And then Z is the collision frequency. So this is the number of collisions that one electron makes per second. Again, normalized by the wave frequency. If we said Z is equal to 0 and we said Y is equal to 0, all of these terms in the denominator would go away, and you would just have 1 minus X over 1, which is the 1 minus omega p squared over omega squared that I showed you earlier. That's the collisionless, non-magnetized version. But the magnetic field means now propagation depends on the direction, the angle between the magnetic field and K, which is the direction of the wave propagation. And it depends on collisions. And collisions also have an I in front of them. Everywhere you see a Z, there's an I. And that makes this complex. And that the complex nature of the index of refraction, again, gives us this term and leads to absorption. So let's talk very quickly, about D region absorption. So if I take this equation on the previous slide and I solve it, turn it into this form, this is your homework assignment. Write this equation as n is equal to a real part and an imaginary part. If you do that, and then you actually convert that imaginary part into absorption. So this is the change in amplitude with distance in decibels per meter. You get this. And so there's some number here that came from constants, electron density times the collision frequency divided by the collision frequency squared, and then the wave frequency and the magnetic field, the gyro frequency. So again, this absorption depends on the magnetic field a little bit and the collision frequency in the denominator, but mostly it depends on the electron density times the collision frequency, product of those two things. So this should make sense. If I have a lot of electrons but no collisions, there's no absorption. If I have a lot of neutrals, so there's a lot of collision, there's a high collision frequency, but there's not a lot of electrons, then I don't have a lot of absorption. So you need the product of those two things. So that's why we end up with a region here in altitude where absorption peaks, because the neutral density, the collision frequency is directly related to the neutral density. So it's dropping off just like the atmosphere. And then here's my profile of the electron density. And at some point, the product of those two things is maximized, and that's where absorption occurs. And that tends to be in this altitude range between about 90 and 105 kilometers. So that's where radio waves tend to be absorbed. It does, of course, depend on frequency. So different frequencies are absorbed at slightly different altitudes, but nominally that's pretty close. I'm running out of time, so I won't show you that. Here's just actually some calculations of that absorption. So I took a bunch of electron density profiles under different conditions. This is actually looking at electron precipitation events where we get enhanced ionization. And we wanted to say, oh, when we get enhanced ionization, how much more absorption do we get? And so here are those peaks in absorption, which do have a slight variation with altitude for electrons of different energies precipitating. There is a device, there's an instrument that actually monitors this on a regular basis called a rheometer. This is a picture of one of them up in Alaska. And the rheometer, it actually just monitors the cosmic radio background at 30 megahertz. And that cosmic radio background has a diurnal cycle. So the blue curve here is what it should be. But when there is enhanced absorption due to electron precipitation, due to aurora, due to flares, etc., you get these little dips in the regular quiet day curve. And so those dips are ways of monitoring the absorption of the ionosphere using this instrument. Okay, the last thing I'll talk about is the effect of flares on the ionosphere. So the same idea is if I have a solar flare with a huge flux of X-rays, X-ray flux can increase by orders of magnitude. Those get absorbed in that altitude range, in that 90 to 100 kilometer altitude range. So they'll increase the electron density there in the lower E region, upper D region, and cause significant absorption of radio waves. This picture is a little bit of a mess, but hopefully you understood what I've just said to you. And so that will be manifested as, again, sort of a loss of communications. This is an approximation of the same equation I showed you for that absorption per unit kilometer. And here's an example where a flare has occurred. They're calling it an X-ray event. It's a flare. And has dramatically increased what's called the lowest usable frequency, as in the lowest frequency that you can use to communicate. In this case, is to use to communicate with over the horizon. So because of additional absorption, you can no longer use those low frequencies. And you can't use the high frequencies because they propagate through the ionosphere. So you end up with a region here, or a time window, where you can't communicate. So flares will do this, and it's largely because of that absorption in the lower part of the ionosphere. Okay, I think I'm out of time. I'm going over time. How do you feel about 2 more minutes?
Well, I was hoping to get.
Okay, why don't I stop? GPS, blah, blah, blah. I'll stop here for questions. Microphone? Oh, wow. That's cool.
We will catch.
Hello. Yeah, I have a naive question because I'm wondering the magnitude of the equatorial electrojet. It's located in the equatorial region, and will it have an influence on the DST index, just like a ring current, or it is influenced by the magnetic storm?
Yeah, so that's a really good question. So for those of you not familiar, the ring current is another current that envelopes the Earth, but at a much higher altitude, at like 3 or 4 Earth radii. And it produces a perturbation in the magnetic field, which can be tens to hundreds of nanotesla during storms, and in the same direction. So you do have these multiple contributions to that perturbation in the magnetic field.
Okay, I see. So
They'll sort of add on top of each other, right?
yeah.
Wait, I have two questions. Just to follow up on that, isn't the DST like a subtracted value? So it's like a change in, so
Yep.
the electrojets are kind of more or less there the whole time, right? So
Right.
if you subtract them out, then there's probably not. It's
Well, so
usually
yeah,
part
the
of
DST index is it's disturbance storm time index. So right, so it is actually a difference from sort of nominal conditions.
Right.
So I'm actually not, I don't know as well how much this one varies.
Okay.
You can see obviously in the densities that the densities are not symmetric around the Earth. So there's definitely some variation there.
Yeah.
So I actually don't know the answer. Is it a perturbation from quiet time, or is it a perturbation from the
Like the
core
day before or
field?
something. Yeah, yeah.
I don't know the answer to that actually.
Okay. And then my other question is, what are other things that change HMF2? Like we said that it varies with solar zenith angle.
Yep.
And then what are other things that will change that?
That's a good question, and I don't think I know the answer to that. You know, there's a lot of other phenomena that perturb the ionosphere and that move the plasma. So gravity waves, planetary waves, tides, those all have an effect on the ionosphere as a whole, and so they're going to move things around, and that's definitely going to change it. On a sort of like localized event basis, um, things like precipitation, I would not think so, because that's typically at lower altitudes compared to the F region. Yeah, there's lots of contributions.
Is HMF2, what's the peak height normally? Is it 400 or
250. I guess I
250?
didn't
Oh,
really say that,
okay.
did I? It's
Right.
like around 250, 300 kilometers.
I thought that with particle precipitation, like green line peaks
Region.
oh
Green line is like
right, and then
100
red,
kilometers.
does red peak at 250 then?
Yes, red
Okay.
line is the F region. Yep.
So then that's kind of around the same, this F2 HMF2 height as well.
Absolutely.
So then that maybe would change that height, or would keep
What
it
do you mean?
about the
Like
same.
the red line itself is just the manifestation of the
Yeah.
air glow, right?
Yeah.
It's the atmosphere glowing. It itself is not going to change. It's not really moving plasma.
Yeah, but if there's particle precipitation, then you're getting like ergo plus aurora. So if you're seeing like an enhanced intensity in red, then you would also see, then there's some plasma change.
It can absolutely change like the altitude of where it's occurring. Yeah, when there's precipitation.
Maybe like atmospheric gravity waves are some sort of phenomena which can change this. Ionospheric disturbances, like from earthquakes or volcanic eruptions.
Yes, absolutely. Yep. There's a lot of research on that, especially in the last couple decades. It's been a huge topic in the upper atmosphere community. Gravity waves, not gravitational waves, but gravity waves. Gravity waves are buoyancy waves in the atmosphere. And they propagate upwards and increase in amplitude, and you can absolutely see them even in TEC data. You can see ripples in the TEC
in TEC and in VLF red.
I'm sorry?
And you see them in TEC, like in the total electron
Yes.
content, and in the VLF waves, like
in the VLF, we don't have the spatial resolution to see that sort of thing. Yeah, no. But gravity waves do tend to break and sort of deposit all their momentum in the lower part of the ionosphere, in the D region and E region. I think there definitely are cases where they get up to the F region, but not as significantly.
Yeah, I have a question about VLF waves. You
Yeah.
mentioned that most of them are reflected somewhere in the D region, so that's why they can be used for long-range communication. But I do know that people do observe some features of VLF transmitter waves on the equatorial spacecraft, like I think One Alien probe. They have.
Yes.
So my question is, do we understand how they can propagate, or how we can detect something that look like VLF waves at the equatorial spacecraft?
Yeah, so that's getting into, again, that's a lot, this is a lot of the research that I do, but the propagation of VLF waves is pretty complicated. You know, in the absence of collisions, they would reflect from some altitude. But collisions actually create a bunch of different effects, including absorption. They also allow the wave to penetrate through the ionosphere to some degree. Even though VLF is way below any critical frequency, something like 20% of the energy leaks through the ionosphere, and then it propagates into the magnetosphere as what's called a Whistler mode wave, a plasma wave. And so those waves actually follow, kind of quasi-follow, not exactly along magnetic field lines, and are seen on spacecraft. So all these VLF transmitters are actually constantly injecting energy into the magnetosphere, where they actually interact with radiation belt electrons. And lightning as well. You see on Van Allen probes, for example, we see they're called lightning generated whistlers, these signals, and we see them all the time. Yeah, would love to tell you more about all that stuff.
Thank you.
Yeah. Microphone.
Is there an advantage of using reflection on certain layer for communication, like using the higher layer for reflection? What's the advantage of different reflection?
Distance and amplitude, right? So let's say if I can use a particular frequency to reflect off the E region, for example. But that frequency might be subject to more absorption in the ionosphere, because the F back in the absorption equation there, frequency is in the denominator. So if frequency is relatively low, you might actually get more absorption. If I go to a higher frequency, I can maybe get up to the F region and refract off the F region and actually communicate a larger distance, because I'm also reflecting off a higher altitude. But you still also have spreading, right? It's not just doing a straight line, it's actually spreading out. So maybe you don't have as much of an amplitude at the receiver. So there's advantages and disadvantages of using different frequencies to reflect off different layers. The biggest challenge, of course, in that type of communications is just predictability. We don't know what the ionosphere is at any given time, so you can't target one particular altitude. You're really just broadcasting a relatively wide beam, and something is going to get to your receiver, right? They would love for us to be able to predict that better. It's a research topic.
And the last question is, can you confirm or deny mind control experiments happening in Alaska?
In Alaska? Absolutely confirm. No, I used to work up there at HARP, and we would get people knocking on the door asking about that sometimes.
Yeah, there's a Wikipedia page on the HARP conspiracy theory.
Yeah.
So you know, which is actually just as a plug, a good plug for better science communication all around, and making sure that people are aware of like the type of science we're doing, and doing outreach when especially even to the local community for these large facilities. So
Yeah, totally.
I think I'm going to call this to a close and
Okay.
call it an Ionosphere lecture. And so let's thank Bob.
You.
And Bob is eminently Googleable.
Googleable?
Yeah, you can be Googled. They can find your email.
Yes.
Okay, right.
You can find me somewhere on the internet.
Yeah. So and so if more questions, or if you have a fellowship proposal that you want to write. But okay, great. Thank you again. All right. Let's do a 10-minute break. So that means be back here by 3:22. Okay, and one way or the other, I guarantee we'll be out of here by 5. Okay, so we'll work things out. Great.